that we're going to go over today with one example. So I'm going to quickly go over all the basics that you might have forgotten from before the break. So we said that for DH convention, our goal is to find the configuration of our end effector. When we say configuration, we mean orientation and position, right? Now, in POE method, you would use screw axis and all that. In DH convention, you're going to use the transformation between each consecutive joints, and you basically walk from them from frame 0 all the way to your last frame, which most of the time happens to be your end effector. We'll talk about that today. And you can use this matrix, which I called it big matrix, if you remember last time, because it's big. And the work is done for you in terms of how the solution looks like. So this is the relationship for frame I minus 1 to I, the transformation from I minus 1 to I. What do you have to find? So if this is the kinematic expression, then what's your job? There are 4 parameters, DH parameters, right? Alpha, A, theta, D. You have to find them for each frame, between each frame. Once you have that, you're done. You just replace it in here. Another thing we needed to do was frame attachment or frame assignment. So if you remember, we said that find all the z-axes, right? So find all the joints, basically, and then assign the z-axis to it. Once you have the z-axis, find the normal between them. Normal is the mutual perpendicular between 2 axes, right? Draw all of those. So you have z-axes, which here are the red lines, and then the normals are the blue lines. So the red ones are your z-axis, the blue ones are the direction, or where your x-axis would lay on. All right. Now the direction of it might change though, but it will be along that. It could be in the direction of that arrow, or sometimes it might be in the other direction. We'll talk about it there. So we lay all those normals. That will be our x. So once you have your x and z, you can find y from right-hand rule. You actually don't need to know where y is because you don't use it, but if you wanted to show, right-hand rule, x, y, and this is, right? We also want to find the origin of our frames. So where your x and y coincide, that's the origin of your frame. So we will put a frame, you can put a frame on that origin, right? So place the origin, find the normals, place the origin, assign z-axis, assign x-axis, you're basically done with frame attachment. Now, once we've done that, we need to find our DH parameter, which is that table. These are all review. I'm just quickly reviewing for you to remember what we talked about. We have joint variables that are theta I and di. Theta if we had a revolution, if we had prismatic. We could also have di and theta. So remember what did we do to specify these are joint variables? We leave a star to show this is joint variable because we could have di and theta I that they describe in connection. You'll see it today. So there could be some existing rotation, there's a fixed rotation or an offset between 2 frames that it does not change, but it's there and we need to account for it. Then we have alpha I and AI, they describe the link itself. There are constant values, they tell us about the configuration of the robot. All right. So these constant values tell about the configuration, the variables are the joint. So still reviewing, just help you to remember. Now, since we are assigning the frames ourselves, we can make things easier for ourselves. First thing we can do is to reduce the number of frames we are dealing with. So if you identify your first joint, all right, and you find the z-axis of that joint, you find the x-axis, and you know where the origin is. you can place your frame 0 on that joint at home position. Find the home position of that joint and say, okay, that is where my reference frame, my base frame is. Now, if your joint start rotating, it is rotating only from the base frame. There's no offset or anything. So a lot of the parameters in your DH table will be 0 because they repel each other. You could do the same thing for your last frame. So your end effector frame could be coincide on your last frame. Then there's no distance between them. So you only need to track your last frame. Why did we do this? Why we are allowed to do that? If you think about your first frame, you did the PA assignment, right? If you had your base frame on the actual base of the robot, there was a fixed, like elevated link, right? Elevation. Let's say L1, whatever that is. That does not do anything to the robot. All the rotation, everything happens from that joint. So we put our reference there, and all you did was, okay, L1, 2 meters from the ground. But all the calculations from there. If you wanted to know now, okay, what is end effector with respect to the ground? Well, add in direction, whatever direction it is, right? Or -2. So you don't need to include that in all of your calculations to make it difficult to yourself. We can do that because you're assigning your own frame. You're making our lives easier. Same for your end effector. So if I want to know the movement, what causes all the motion? All the joints. So if I know what is the effect at the last joint, if my end effector is, let's say, 5 centimeters away from it, I'll find that, and then I'm going to manually add, okay, now 5 centimeters in the right direction, because that's what actually end effector is. That last, if it was a fixed link that didn't move, you don't need to bring that into your calculation because it will be some V plus a joint variable. Why would you do that? Does that make sense? So you want to make your life easy. Now someone say, I don't want to, I want to get the final solution. Okay, do it. I won't say don't. And you will see some, if you look at the examples online, which again, I told you do it. Go check and then solve some of those examples. You'll see that they get their base frame separate from their first frame. It's fine. You can do that. But you have to be careful. If you do that, your DH table will be different from someone that didn't do it. But both of your solutions will be the same. Meaning that if you simulate it, they will act the same. All right? All right. So here is when your ground frame or base frame, frame 0, coincides with your frame 1. So let's say you had a revolute joint. So if blue is your base frame and red is your frame 1. At time 0 and theta 0, both of them, so if theta 1 is 0, both of them in the same direction, right? Now, since the rotation happens around the axis, if theta 1 starts being anything above 0, greater than 0, you only have theta variable. AI, alpha I, DI is 0. You only have in that table 0, 0, 0, theta 1 star. Super easy. All right. If you had prismatic, same 0, 0, 0, D1 star, because that's the only way that frame 1 is moving away from 0. I'm just going to show you, if you don't remember what that table is. So this was link I, let's say for the prismatic case, alpha I minus 1, AI minus 1, DI theta I, right? This will be 0, 0, D1 star 0. You could write similar thing for the revolute part as well. I have it in my annotated version for you, so if you wanted to reference to that. For the end effector frame, similar. You could have your end effector to coincide on your last frame, or you can say, no, it's away, but by an offset. So you will have an extra D, but everything else is 0, because there is no value there, right? So time for an example. So I want you to kind of get started in this one. think about how many joints do you have, and try to create the DH table and see if you can write the parameters. You should always be able to follow those four statements to fill out your table. The first one is AI minus one, the second is alpha I. So in your table, I'm gonna draw how the table should look like, but I want you to fill it out. So I will let you figure out how many joints we have. But this is, let's say AI minus one, alpha I minus one, DI, theta I, and yes, the first two are one subscript behind the other two. So it would be frame one, and then you go from there. Again, the frame are assigned here, and the goal is for you to fill out the table. So quickly, look at frame 0 and frame 1. Tell me if you can fill out the first row very quickly. Yes? 0, 0, 0, theta. All right, I'm gonna go walk around, see how did you fill that out. Kind of draw what would you have to do. All right, I'm gonna walk you through the row 2, and then you can do row 3 by yourself. All right. Even at this point, when I want to fill out the DH table, I put those 4 things in front of me, and I draw the axis. Because I don't want to make mistakes. All right. So I invite you to do the same thing every single time. If it was an exam, it will help me to understand your process, and it's easier to grade you. You make a mistake, I know where it comes from. For you, we need to practice it. So we are going to start from top, frame I is 2, so I minus 1, A2 minus 1 is A1, right? So we're gonna find A1. A1 is the distance between Z1 and Z2 along X1. Yes. It's a joint variable. And you will see why we separate them right, like once I fill out row 2. Okay. Yeah. Give me a little bit. All right. So for the first one, what is missing? What do I need to add? I didn't show X1 yet, right? So it means that whatever distance I find, the positive direction is along X1. It's I minus 1, right? So X1 is in this direction. Do you see that up there? So what I did is I brought the axes on the outside. So this is my X1. So the distance between Zi and Z2 in this direction, L1, right? The distance between Z1, Z2 in the direction of S1. That's 1, I found that one out. So that's going to be L1. 2. Alpha 1 is the angle between Z1 and Z2 about X1. X1 is still here in this direction because I know this is Z1, this is X1. And all I did is I kind of shifted X2 so it's easier for you to see, right? Now, a lot of you put 90, right? I want you to be careful. You need to pay attention to the positive side. You were correct. Either you did pay attention or you just got lucky. The positive direction is about X1. So your thumb is where X1 is, and you have to close Z1 to Z2. If that's the positive direction, yes. So what if someone wrote like negative 270? Okay, so I won't do that. So this is the positive direction. You won't get lucky every time. Sometimes it's the other way. So this is, yes, 90 degree because this is the positive direction. It is very important because sine of pi over 2 and sine of negative pi over 2 are different. Yes.
Let's say, like, what if E was a long exponent? What would the outcome?
It won't be like that. Why? We are defining the axis. We're not going to mix this. Right? So that's why we are deciding whether to use right or forward. Why we are doing all this finding forward kinematic expression, right? So in forward kinematic expression, the configuration of the robot needs to show, because then it will impact the simulation. So if you eliminate an joint that does not appear in the forward kinematic, you can show it moving. So we choose these frames so that our solution will make sense and we have everything. But there are cases they will be in the same plane and then you will have to treat them differently. All right, now for DI, DI is the distance between x1 and x2 along Z2. Z2 is here, right? They are coincide, so there's no distance, 0. So we get here. Last one that almost half the, I didn't see your lips. 3 of you got it right over there. And you got it. All right, so this is answer to your question, why theta star and theta are different, or why we bother. Theta I is the angle between x1 and x2, right? About Z2. Let's find out where Z2 is. This is our Z2, right? Pointing outside. So this is pointing outside, and we're trying to find the angle between these two. Now, this happens to also be a revolute joint here. So we want to know first if there is pre-existing angle between our x-axes, then we apply our joint variable to it, right? So if you look, the x1 and x2, they have a pre-existing angle. So the direction of rotation is here. You have to put x1 goes to x2. Now, you can also negative pi over 2, right? It's either 270 or 90. Either one works. So this becomes, so I'm going to write negative pi over 2, it's easier. So those 4 are to tell you the configuration of the robot. Now, all of these eyes, they have joints, right? What's the joint in, what's your joint in front 2? A revolute joint, theta 2, right? Could be a positive or negative value, we don't know, that's why we write theta, anything can go in it, right? So I can say this pre-existing angle between the two plus theta 2 star. Meaning that when this starts to rotate, this is gonna go this way, right? So it's gonna kind of cover, go to x1 and then keep going. So this is where we show the configuration and also joint. Does that make sense now why we show part of it with this star, part of it with theta I? So this is your theta I from those statements, the configuration of the robot. This is, if the user said theta 2 goes to 35, now you add 35 to this. That becomes the position at that point. Same thing will happen when you have the prismatic. There could be a pre-existing offset. Then that the joint will then go maybe cover that offset or goes from that offset. But you are thinking about the positions, right? So you need to tell the controller that where this joint initially was, and then we are adding 2 more centimeters to it, or we are going 2 centimeters toward from where it was. Since we can't communicate in English with the computer, you write this code and it says, right? So these 2 are very important, this, and when you have the I. Now do the third one. Yeah. So I suggest kindly do what I did, draw that. Drawing 3. It was -1, yes. L2, negative pi over 2 or 270, 0, theta 3 star, there is no offset. Ta-da. Good. All right, so this is your DH table. Do we stop here? Big matrix. Thank you. So the goal is our forward kinematic expression. But it's almost there, so we need T0 to 3, right? You see where did I put the end effector? I put it on the last frame. Yes.
Why is there no offset?
I will draw that. Let me finish and I'll draw it. All right. So, because x2 and x1 are in the same direction, there's no angle, but I'll draw it. All right. So T03, you see that I put my last frame B on frame 3. Could I say this is like there's a distance? I'm gonna put it here. Yes. What will happen? There will be a D in the 4th row, 0, 0, the D, a fixed number, because it's not a join, there will not be a D star. So I'm adding one more matrix. My calculation, why would I do that? I'll tell them that I found it up to here. Because you actually don't know what the risk for your end effector looks like. We usually solve them separately. So here we will have T01, T12, T23. Each of these, we have these parameters. We plug it in our big matrix and solve. In your exam, in your homework, that's what I mean. If I said that calculate this T03, you go to MATLAB, you code your big matrix, create 3 vectors, plug those in, and tell me that's the final answer. You don't have to read my. Make sense? That's the whole idea. You work just to find the parameters. Now, to answer the question, why theta 3 star doesn't have any offset? So, can I draw? Let me clean these things a little bit. All right. So for I equal 3, let's find theta 3. To find theta 3, angle between x2 and x3. This is x2. This is x3, right? I need to find the angle between them along Z3, which is in this direction. X2 and X1 are coincide like this thing, so there's no angle between them. Like it was a slightly, I don't know, for some reason here, then you had a whatever angle on the 45. This is the configuration of the robot. In the annotated version, I have done all of those for this one as well. So if you couldn't follow what happened, you will see that in a minute. I want to talk about one here. One special case when Zi minus 1 and Zi coincide. So let's say this is your Zi minus 1 and this is your Zi, meaning that, and then they are in the same plane. Why is that important? Because we draw our x, where is it? Here. We need to find the common normal along those, between the Z axis, right, to draw our x axis. Make sense? Now, when you have this scenario, which way is the x axis? We need to find a common normal between that. So these two are, they coincide, right? Where is x axis? It has to be normal to both of them. This is here. Either one's fine. You just have to show that these could be 90 to both of them, right? It could be in this direction, could be in this direction. Now, why does it matter? Because when we are measuring, finding our DH parameters, you measure some of them along x-axis and about x-axis. Now, if you draw here or draw here, your answers will be different. But it will match the direction you consider. So once you have your transformation, it will correct itself. It will account for the extra, like the 180 degrees difference. Which way do we pick? 0, right? So if you would have a 0-degree angle versus 180, so you would go with the 0-degree angle because like some of the value becomes 0 in your measure. But it's not wrong if you put the other way. All right. So you have one slide before this, right? Slide. So I think I'm not, I did the version. I put the solution of the 3R robot that was in your previous lecture, and it was also an annotated version of that. Did anybody review that? Does anybody have a question on that? The only difference between that and 2R that the solvers, you have to do one extra row. And since all of the Z-axes are in the same direction, that's very simple. Here you see that once you have the axes in different directions, they're not parallel with each other, you start adding numbers, sorry, not here, start adding numbers in your table. Why this table has so many numbers here and the other one that you saw was all 0, 0? Because your axes are not all parallel anymore. You start seeing those opposites and angles. So review the 3R as well. If you have a question, let me know. Should be straightforward because it's easier than this one. If you understood this one, all of those are a lot easier. Now, your class participation for, well, your checkpoint, let's call it checkpoint. Here, this is your base frame, and you see that this is the example of the traditional method that you see the frame assignment is different traditional method. I put this here to show you this is also acceptable and you see that. So here, this is your first joint, and they place the axis up there, the frame. Can they do that? Yes. You're assigning it, right? As long as you're following the rules, the rotation happens about the z-axis, and the x is the normal between the two z's, you're fine. If you start looking for your assignment online, you'll see these. For your homeworks, I don't accept these. I accept what I introduced you. Did everybody hear that? So I accept for your homework what I taught you. But I'm also introducing and presenting you what you can find online. These are correct, but I don't want to teach you two things. So that's why I assigned this frame, so you don't have to do different assignments. You just follow your rule, fill out the table. Any questions? You're confusing, yes.
So we're moving just graphics. I'm guessing D1 is like.
So this is a fixed
Right.
distance between this frame and that frame.
Right.
This is your frame right variable. If you see that two headed arrow or one head arrow, it means that that thing is moving. Okay, so this you could put any value for D1 because it's a fixed distance between the two base frames, the two frames. It's the configuration of the robot. You could have, so here's the thing. Once you know, so this robot is what? RPP, right? It could be different the direction of movement, so there would be different robot, different configuration. But this RPP could be in different scale factors. Could be a small tabletop robot, could be a big industrial robot. What's the difference between them? The size, right? And joint torque. What motor you put. The dynamic and the kinematic is the same. That's why when we're modeling, a lot of times you see there is L1, A1, D1, because we really don't care. As long as we assign them a value later on, we don't care. Kinematic tells us how things move with respect to each other. So for this one, D1 is a fixed value. Just the distance between these two is an offset, right? D2 is actually a joint variable. D3 is also a joint variable. D4 is a distance. Now, if you're calculating and you needed to know, I don't know if there's extra distance between frame 1 and frame 2, you think is missing, assign a value. 3 doesn't matter, it could be 0. You can literally say, it says P1, fine. I'm going to say P1 is 0. Does that make sense? So this could be that those two are on top of each other. There's no distance between them. You don't like it, you feel more comfortable putting distance between them for P1, and then you can later on say P1 0. Make sense? So a lot of things here are your understanding of how this robot looks, how does it move. The kinematic is just to find that expression that matches. All right? Look at CP13. The robot is that one is for velocity kinematic, what you learned last time. So no axes. So you have to sign. Don't look it up online. The directions are wrong. You can, but the directions won't match what we talked about. All right. That's all I had for today. I'll see you on Wednesday. Just study, make sure that you got this. And come pick up your exams. Here and 8 to stay here, so we don't have everyone the same place. Alphabetical from last name.